Section 2.4, the discovery of the electron. So J.J. Thomson, back in the late 1800s, early 1940s, created a cathode ray tube. He constructed a cathode ray tube. Here's a photograph of one, here's a diagram. So there's this glass tube that's partially evacuated. There's a little bit of gas in there. And there's an electrode at each end, and those electrodes are connected to a power supply. And what he found was, if you put a high enough voltage across the gap here in this tube, you can get a beam. It looks kind of like a beam of light. You can see it sort of in here, this line in the middle. That's the cathode ray. And the cathode ray was a beam of particles, and it moved from the negative end, the cathode, to the positive end, the anode. And of course the question was, what is that? He found that those particles have some properties. They always travel in straight lines. They are the same regardless of what the material of the cathode is made of. So you could make the cathode out of aluminum or out of iron or out of gold, and the cathode rays are the same. He also found that the cathode rays had a negative electrical charge. So, brief trip to physics, what's electrical charge? Electrical charge is a fundamental property of some particles. And it results in attractive and repulsive forces. Electrical charge is different than magnetic fields, and yet they act in some of the same ways. So we have experience with magnets, right? You put a magnet on the refrigerator. You mess around with two magnets, and if you put them one way, they stick together, and if you put them another way, they repel each other. Electrical charges behave similarly. Opposite electrical charges are attracted to each other. Like charges, two positively charged particles are going to push each other away. They will repel each other. When you have equal positive and equal negative charge and you put them together, then overall that combination has zero charge. Bless you. So these cathode rays were composed of particles with negative charges. He was able to measure the charge to mass ratio by deflecting the ray using electric and magnetic fields. So here's the cathode ray being formed, and it's shooting out into this tube. Here he's got a magnetic field, and there's also an electric field in here. And so by changing the magnetic and the electric fields, he was able to deflect the beam. And by measuring the amount of deflection caused by the amount of field applied, he was able to figure out that there was a charge of negative 1.76 times 10 to the 8th coulombs per gram of particles. Now that number by itself is not all that useful, but because we knew that, someone else was able to learn some important things. So this implied that the cathode ray particles were about 2,000 times lighter than hydrogen, the smallest known atom. So if the atom is the smallest particle of matter and the atom is indestructible, how could we have these particles that are so much smaller? This was huge. They thought of it as being the atom being chipped away. So you could spit off little pieces of those atoms. Those little pieces were electrons. So electrons are negatively charged particles. They have very low mass, and they're present in all atoms. That's why we get the same kind of particles no matter what the cathode was made out of, because all atoms have electrons. So this was the first evidence that atoms are actually composed of smaller particles and that those are the same across all the different elements. 1909, an American physicist named Robert Millikan performed an experiment that, combined with Thomson's information, allowed him to figure out the charge on a single electron. I have a video that kind of shows how this thing works, but I'm going to tell you briefly about it first. So he's got this setup here where he's got a positively charged electric plate here and a negatively charged electric plate there. Here he's got an atomizer, like you would use with perfume, to form a very fine mist, and he's spraying tiny droplets of oil into this chamber. Of course, they're subject to gravity, so they get sprayed out and then they begin to fall. There's a teeny tiny hole here, and some of those oil droplets will fall through the hole. The rest of them just sit on top of the plate. So the ones that fall through the hole are going to get hit with ionizing radiation, which is going to cause them to have a charge, a negative charge. It's got a viewing microscope and a light source. Now that these particles have a negative charge, they're going to be attracted to the positive plate. They're going to be repelled by the negative plate. So if he adjusts the charges just right, he can cause those particles to be suspended in air. And looking at those charges allowed him to figure out what the charge on a single electron was. So let's look at this video. Okay, fine.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhere to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Not a very dramatic ending there. Any questions? I do not expect that you get all of what that video said. It comes at you really fast and all these equations and thus and therefore and blah, 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 and ta-da, right? What I like about that video is it illustrates one of the cool things about science. A lot of science is not about just measuring something and being done with it. A lot of that stuff has already been done. Now we're trying to find these things that cannot be measured directly. And so you have to find very creative ways around that. You cannot measure the mass of an electron. It's too small. You can't measure the charge on an electron. But this guy came up with a way to figure those things out. And I just think that's really, really cool. So I am not going to test you on Millikan's oil drop experiment. I want you to have heard about it. There are a lot of other really, really cool experiments that were done, and we just don't, it's not a class in chemical history, so we're not going to go over all of them. Yeah.
So 1909, where did you get was the X-ray like a thing back then?
X-ray was a thing back then, yeah. I don't know that they were using it on humans, but yeah, radioactivity had been discovered. Yeah. And, you know, here they are playing with X-rays and stuff. A lot of these scientists died much earlier than the average life expectancy because they were doing experiments with dangerous things that people didn't know were dangerous. So he was looking at the strength of the electric field needed to halt the fall of the drops. So you've got gravity pulling them down, and so find out what strength of electric field is required to keep them from going down. The gravity is dependent on the mass of the drops. By knowing the mass, then he could calculate the charge on each drop. So some drops may have had 1 electron extra, some might have had 2 or 3, and so he got lots of different charges on these drops. But he found that any of those drops had a charge that was a whole number multiple of this same wacky number, 1.96 times 10 to the minus 19 coulombs. They were all multiples of that, and so that must be the smallest electrical charge, a single electron. So having that and Thomson's mass to charge ratio for electrons, he was able to calculate the mass of the electron, the charge times the mass over the charge. So here we've got the charge on electron, and then we have the ratio of charge to mass, and he was able to calculate the mass of the individual electron.